Yeah. The left, on the left, to the left. Yeah. To the left.
Very manipulated.
This is
Oh, that one. Okay. So I think we can start. Today we are happy to have Alfredo as our seminar speaker. Alfredo did his PhD in parameter with Freddie Picasso, and after his first postdoc at Harvard, he's now joining IAS for his second postdoc. So yeah, please.
Thank you. Thank you. Thank you for the invitation. And very nice to be here for my first time, other than the boring East Coast of US, especially in this weather. So thank you for inviting me, not in wind. Yeah, so the title of my talk has something to do with black holes and self-duality. So my boss in Princeton used to say that he's not a mathematical physicist, he's a physicist who loves mathematics. So I guess I should say I am not a string theorist. I am a physicist who loves string theory. And I actually do love astrophysics as well. So this will have something to do with astrophysics and something to do with string theory, or at least motivated by string theory. So let me just describe what is self-duality. Like, what do I mean by this self-dual solutions? Well, the way I think about it is a bosonic version of supersymmetry. So we all know and love supersymmetry. We use it to construct very important and nice mathematical structures. So the string theory is part of that. But we want to have some version of that that actually doesn't imply Grassmann variables, that doesn't involve supersymmetric states. So this is why self-duality is a bosonic version of supersymmetry. Well, I haven't told you what self-duality actually is, but I guess you will have an idea after these points. So the first one is that we want something that has extended symmetries. So usually that means there is a notion of integrability if there are enough symmetries to constrain the phase space of a theory. And one important paper in terms of self-dual gravity was actually explicitly computing amplitudes in that theory, was the 2013 paper by Monteiro and O'Connor. If you come from a supergravity background, you will know that there are certain protected solutions where we can do computations. These are called the BPS states. And these BPS states, they arise in 11-dimensional M theory and can be reduced to supergravity and so on. But in particular, there is an imprint of those at lower dimensions, including 5 and 4 dimensions. There are certain solutions that are reduced from these BPS states. That means you can do calculations in the M theory regime perturbatively. They extend because they are protected. So you can compute things like the spectrum and then reduce them and check some predictions and consistency in 4 dimensions. And in 4 dimensions, I would argue that they happen to look like self-dual solutions of gravity. Other interesting things happen when you have supersymmetry. Once you compute path integral, the action turns into a boundary term, which is kind of magical in that sense. And this allows you to compute exact amplitudes and exact spectrums from localization. And maybe last but not least, the simplicity in certain formulations. I'm not going to describe this. This is essentially just to advertise one of my recent papers. But if you have ever heard about perturbative gravity, you would know that there is some important formula. It's just a single term that computes gravity amplitudes. And it goes by the name of Hodges' 3-level MHV gravity formula. And we just expanded. We sort of justify that formula in this recent work. But this talk is mostly going to be about these 2 points. The fact that there are certain exact protected solutions living somewhere in the UV universe that we can dimensionally reduce and analyze and understand and derive astrophysical predictions from it. And the fact that we can compute exact quantities like scattering amplitudes, yes.
So I still don't understand what you mean by a bosonic version of supersymmetry.
Yeah, yeah.
Supersymmetry relates fermions and bosons.
Sure.
So if you have a bosonic version of that, you don't have a supersymmetry. I mean, I don't.
Okay, this is just a slogan.
Yeah, I know.
If you let's just maybe forget about the actual title, but there are like at least 4 things that are present in supersymmetric theories, which I would argue that are present even if we don't have supersymmetry. Yeah.
I know you invited us to forget it, but is there some notion of grading? I mean, is there anything that this slogan actually captures?
Yeah.
Apart from that, it's nice. But
No, yeah. So the precise statement is that there will be some KK solutions coming from BPS states. Those have super multiplets, and super multiplets allow you to solve, equations of motion for different states in one.
super multiplets in terms of supersymmetry, in terms of duality.
In terms of supersymmetry.
Yeah. So
But and in which sense is there anything like a bosonic motion of supersymmetry? What do you mean?
Like if you consider certain bosonic, so let's talk about a black hole. Right? So we have a BPS state. We know that it's a supersymmetric vacuum. There is some Killing spinor and so on. And you can use a Killing spinor to construct bosonic solutions like a spin 1 field, spin 2 field solution in that background. So in that sense, that's a sort of
that's a supersymmetric solution in supersymmetry.
Yeah, that's a supersymmetric solution, but it's mostly bosonic. I mean, we just care about the bosonic part, and actually.
Okay, right. Fine.
Yeah,
I mean, that's
yeah,
then I'm happy.
Yeah.
So
Okay.
there's still fermions there. You're just ignoring them or decoupling.
Well, we don't know. So okay, let me just put it this way. There is a sense in which these theories are integral, and integrability is it's in a sense an umbrella for supersymmetry. So supersymmetry actually gives you certain integral theories, but there are much more integral theories than supersymmetric theories. We believe so. If things like the Ward conjecture, so this goes into the realm of this twister stuff. Things like the Ward conjecture tells you all the integral theories, all integral field theories actually come from dimensional reduction of super-Yang-Mills theory, in some sense. Then maybe supersymmetry actually is present in some hidden sense, but we actually don't know. So actually, the question of whether integral theories can be supersymmetrized or not is it's a very interesting question.
Yeah, maybe then you mean more accidental SUSY, right? Because if you take the instanton, QCD instanton, right, it's accidentally supersymmetric because I can put the gluino to 0 and I still have I could add in the gluino. I mean, it's still a solution. So is that the sense you mean here?
Yeah. But we don't know if there is a gluino in general. So if I give you an integral theory, I give you the KBV equation that has a hierarchy of integral charges. So can you tell me what's a supersymmetric version of that? There is a hint in the fact that the spectrum is degenerate. So there are things you can compute, and you can suspect there is supersymmetric parent of that, but we don't know in general. So I mean, morally speaking, all of these theories are inspired by supersymmetry. But first I should describe the theory. So if you allow me to, yeah, that's kind of what I want to stress. So it just happens that these BPS states we construct in 10-dimensional supergravity, for instance, are self-dual. So what self-duality means is that I will look at the four-dimensional Riemann tensor, and I will find that either taking the Hodge dual gives me plus or minus I times itself. Okay, this is in Lorentzian synchrotron. So that's kind of a condition similar to gauge theory. If you look at the dion, for instance, the dion has a curvature, a field strength that is self-dual, depending whether the electric charge is equal to plus or minus the magnetic charge. So you would suspect there is something like that here. But interestingly, these self-dual actions that impose this condition can be perturbed. So actually, not everything. So now we're entering the region where the integrability is broken because we can perturb Einstein equations around these solutions, and these are usually considered Euclidean instantons in the path integral. But we will see they have a more interesting interpretation. So all of this idea comes from an old story by Penrose, who tried to quantize gravity starting from these solutions as the vacuum. So you would find some Gibbons, Hawking states, whatever, and try to perturb them around. There's some kind of controlled perturbation theory around those states. And we will revisit part of that. Okay, and that happens in the gravitational theory, but we know that the most interesting things, arguably, about gravity are black holes. And in this particular talk, we will relate this notion of self-duality to one of the most interesting properties of black holes, which is extremality. Okay, so let me just give you 2 punchlines in case we just need to set a little the framework. So the 2 punchlines are the following. So at first, you look at self-duality, right? So you look at solutions that satisfy this condition in gravity. What we will derive is a new equivalent formula involving a background that has the analog of the magnetic charge. Is called the NUT charge in a gravitational theory. And what this formula gives you is the amplitude. Okay, so maybe I should draw exactly what I'm computing. So imagine you have a black hole. The black hole, oh, I think I draw it there actually.
So hard to see. Can you draw it bigger?
Yeah, sorry. So the black hole has a spin, if you want. It has some spin, A. Let me just call A the axis of rotation. And then there is a cosmic string attached to the black hole that carries a charge. That charge is labeled by N. It's called the NUT charge. So this black hole has a mass, has a spin. It doesn't have electric charge, but it has NUT charge. And the way we think about it is the magnetic charge is essentially the NUT charge in gravity, and the electric charge is essentially the mass in gravity. So if you remember things like the Noether theorem, they tell you actually black holes only have mass and spin and charge. It's actually true, but if you allow this mass to be complex, this NUT charge is like the imaginary part of such a mass. So just like in QED, we usually consider e to the I plus g to be the effective charge of a dion. In a black hole setup, this would be m plus ion. Okay, so the Noether theorem is still true, but you need to consider complex deformations.
In identifying the mass with the electric charge, are you assuming extremality? Is this an extremal one?
No, yeah. So extremality here. Okay, so let's talk about the dion. So for the dion, we say the dion is self-dual when E is minus Ig or minus plus Ig. And in this case, the black hole is self-dual when M is plus or minus Im.
Sorry, I don't immediately understand. The electric charge and the magnetic charge are real integers. So what do you do?
Yeah, so they're integers, but they can be the same.
Okay, but there's an I.
Yeah, so we need to, yeah, exactly. So we need to analytically continue. These solutions are actually not real solutions. So in fact, they appear when you look at the saddle point of the Euclidean path integral, not the Lorentzian path integral.
Okay, so this is a generalized black hole solution, it's complex,
Right.
and then can you say a bit more for
Yeah, yeah,
friends in the audience? What is
yeah.
this?
I will say a little bit more. So the defining equation of, so let's just look at the defining equation of this. Let's take the Hodge dual of F, and we will find that if E is I plus G, the Hodge dual is I times F.
Yes, I'm familiar with it.
Yes. But that tells you that F cannot be a real tensor, right?
Yes,
F has,
in Euclidean.
Yes.
Oh, sorry. Minkowski.
This is actually Minkowski, yes.
Minkowski, I'm sorry. Yes, that's true.
Yeah. In Euclidean signature, actually you have, because the Hodge dual is square to plus or minus 1,
Yes,
you can actually have this
that's right.
kind.
That's right.
Yeah.
Yes, I was told.
So let's talk about the gravity case now. So if we impose this condition of self-duality, that tells you that the metric actually cannot be real. And in fact, it's not real because the mass has a binary part. So if you consider the Schwarzschild solution, but you impose this condition, you will find that the mass has to be complex. And for this to happen, it must be that m equals plus or minus IM. So that's a self-dual solution. Now, why is it interesting? It's because in these backgrounds, we can compute things. We can compute much more things that without without the NUT charge. So we can use them as some kind of a vacuum, in a sense. I will hopefully describe what that means, to do perturbation theory around.
It's a question.
Yeah.
Another question. So in Yang-Mills, we know that this corresponds physically to tunneling between vacua. So does the gravity self-dual, does it have some interpretation?
Very good, very good. Yeah. So these cells are usually called instantons in the Euclidean section. There is a sense in which we can compute the transition amplitude. So actually, this is what Gibbons and Hawking were thinking about. So the most famous examples of these things are Gibbons, Hawking states, sometimes called multi-center solutions. So there is a sense in which we can compute a transition amplitude between these Gibbons-Hawking states and the vacuum. But yeah, so
that's kind of like the background for these kind of solutions.
This is how they came up. Yeah, so people were trying to do an integral in gravity, and they need to find saddle points that are exact, and these were one of those saddle points that are complex. Yes.
Right. And is it obvious that they have a non-zero Stokes multiplier? And if you have some random complex solution, it's not always computed.
Yeah. So actually, we don't know. We actually don't know how they contribute to the band integral. Yeah. Yeah. Anyway, so what this formula here reflects, without going into much details, is the fact that we can calculate things on these regimes, on the fact that we have a self-dual background with mass and charge being equal. We can compute a scattering amplitude of a wave coming in from infinity, from asymptotic non-infinity, and then scattering with some momentum k.
Is it a gravitational wave?
Yeah, it's a gravitational wave, but it can actually be anything. And in fact, the formula is the same. Again, it reflects the fact that we can calculate things easily in this background. What you need to add, so this is, if you have ever calculated these eikonal integrals, they usually have eikonal phase. This can be considered a phase shift in S matrix. This eikonal phase is integrated over an impact parameter. So the impact parameter is just the effective distance between the wave and the object. You integrate over that, and then you have to do some Fourier transform. That's the usual thing. The new thing of this formula is that it depends on Q, which is essentially the NUT charge times the frequency of the wave. So this is kind of an exact solution that depends on Q. The interesting part to me is that it if you actually restore powers of G Newton, this space is all powers of G Newton just because by dimensional analysis, this has to have a G Newton here. So we say it's post-Minkowskian in the sense that it contains all powers of G Newton reason. So this solves the Minkowski equation. If you compute perturbations of black holes in GR and rotating black holes, they are controlled by the Minkowski equation. We find that in a self-dual background, it has exact solution.
May I just ask, phi is the frequency? Is that-
Oh, sorry.
And what is P? I mean, what are the symbols?
Oh, pi is pi. Yeah, pi is.
No, I just, P, not pi. I'm familiar with pi.
Oh, p. Sorry, p is the momentum.
No, P, K is the momentum.
Yeah, sorry. No, p is the momentum, but it's the for this purpose. So, sorry, this formula I was taken from paper. P is actually the momentum of the black hole, which is essentially the mass.
Okay.
So
And phi is the frequency. You said phi.
yeah, phi here is the angle, is the azimuthal component of B. B is a 2 vector.
I see. Thank you.
And so again, if I wanted just to understand, if I connect it to Yang-Mills, this is a wave scattering off a dion. It's
Yeah.
equivalent.
Yeah, exactly. Yeah, in fact, the same formula is valid in that case. Yes. Yeah, I could have completely reconstructed the talk in terms of dions, and part of the magic in this case is that the dion is exactly. So people know that dions can be mapped to gravity. Sorry, in some sense, the Schwarzschild solution is like an electron because you solve the equation of motion in a Schwarzschild background, you find a Newtonian potential plus G squared correction, right? So if you solve the equation of motion in the Schwarzschild background, you find an effective potential that has the Coulomb interaction plus a G squared correction that depends on the angular momentum and so on. And this part is kind of the general relativity effect. What so happens is that once you add G times N and G times N, this part cancels in a sense. So the question becomes essentially a question of the Coulomb potential. That's why we can write these exact formulas. After we add this NUT charge, all the effects of the gravitational higher order interaction actually cancel, and that's sort of what underlies such a simple formula. So in that sense, we call this black hole the hydrogen atom of gravity, essentially because we can cancel the fine structure correction. So if you were to compute one loop and so on in the hydrogen atom, you will find this fine structure correction, you will find the Lamb shift and so on. In this case, when you consider a dion, such corrections are not present.
I have a question.
Yes.
So in this case, the potential is just something 1 over r. So it's like a closed orbit.
No, 1 over r has open orbits as well. Yeah, it can be elliptic, and the interest. So obviously you can have elliptic and hyperbolic. If you were to compute elliptic orbits, you will find that they precess, and this precession is controlled by this. This precession is controlled by these G squared terms. And it so happens that after you cancel this, actually, there is no precession. So in this black hole, there is no precession. And that's an imprint of integrability again. So again, we're back at the original story of Kepler discovering ellipses because they can be integrated. And actually, in this black hole, you can actually integrate them as well. Okay. Let me just move to the second point, and maybe I can wrap up the talk with these 2 points. I will explain them obviously, but I think that's gonna be it. The second point is the near self-duality. We still have some kind of imprint of self-duality. So let me explain what near self-duality means. Well, near self-duality is just the fact that we can expand Einstein equations around this point. In terms of the mass and the NUT charge, it would be like giving a small deficit to the NUT charge. Okay, and we can ask what happens at first order in epsilon, right? Now, one thing we find is that this epsilon is like, in a sense, like the temperature of, is the Hawking temperature of this state times a redshift factor that I'm not gonna write. But the sort of moral of the story is that as soon as you perturb, there is an inner horizon, and so you can compute the temperature, and in fact, you find that it matches the perturbation. So these black holes are very cold, and cold black holes, usually called extremal black holes. Extremal black holes are defined to have 0 Hawking temperature, have some interesting property. So this property was found long ago by Horowitz and other people, I think Gibbons as well. And what they have is that they have an infinite, so as soon as you come close to the horizon of these things, so you come close to R plus, say, there would be a throat. And the throat is essentially the region near the horizon. And it happens to usually have an SL2R algebra of symmetry. So there is an ADS2 component of this throat. If you look at just the radial and temporal component of the metric, there will be some ADS2 direction. This ADS2 has SL2R. For reasons that have to do with the literature, we call this love symmetry. I will explain why is that. But sort of the moral of that is you have some system at low temperatures develops an emergent symmetry. That symmetry is conformal symmetry. And we know that happens to certain condensed matter systems at critical temperatures. So actually, there's a sort of idea here of relating this to a critical temperature of a condensed matter system and show that these emergent symmetries actually allow you to calculate the CFT that lives in that region. Okay, I'm not going to explain what exact means. The story of love symmetry is one of the examples of things that you can compute. So black holes have what's called the love numbers, and those have been sort of studied in the recent gravitational wave literature. So these love numbers, again, I'm going to explain everything as if we were doing QED. So in terms of QED, what these love numbers are is the susceptibility of with respect to let me just call it F. Let me just call this sort of the dipole moment. Okay. In this case, it would be a quadrupole moment, but you know, we're squaring everything, right? So if we were doing QED, we would look at the susceptibility of the dipole moment with respect to electric field. In gravity, this will be the quadrupole moment divided by the strength of a gravitational field. So I should.
So can I understand it as like a tidal deformations?
Yes. Sorry. Yes. For gravity, it would be a tidal deformation because the quadrupole measures the tidal effect. So obviously, black holes as a starting point have a there is a quadrupole formula for them. As soon as you deform them, okay, I'm gonna. Is
this explained in detail somewhere in your talk, like in the slides?
Part of it, yeah, part of it. Yes.
Part of it.
Yeah. So there would be a black hole that is acted on by some gravitational wave. Sorry, let me just call it H. And as a response to that, the gravitational wave, there will be some deformation that's measured by the quadrupole moment. Okay. So this quadrupole moment depends on H. Okay. This is like the simplest version of the love number calculation. The only thing that's sort of different in this case is that we compute this at zero frequency. We compute this at very low energies. So this gravitational wave here has low energy. And in that case, we can make a prediction These are called the static log numbers. For the
Is log
case,
somebody's name, I'm sorry, or is it?
yeah, log is somebody's name.
Somebody's.
Yes.
There are a lot of jokes about that. I've heard.
Of course.
Yeah, people say black holes have no log and things like that. Yeah.
Right.
Yeah. Or this. Then you can measure these things in the gravitational waves, and they call it the tune, the sound of love. Okay, there, you can make an unlimited number of puns with this person's name. I'm not sure that person will be happy, but he passed away a long time ago. Okay. Okay. Another version of this log number calculation is quasi-normal modes, but it's essentially the same story, so I'm not going to explain that. Okay. So those are the two punchlines. There will be a Conan formula, the amplitude at the self-dual point, and then we will do something around the self-dual point. That's essentially the whole thing. Okay, so why we care about these things? As I said, you can compute path integrals in gravity, and you care about what the saddles are, even if they are not real. In particular, the self-dual states are not real. But every time we have a GR solution that's exact, for me, it's kind of a little miracle. Like, you're not expect to have like a PDE with exact one-line solutions that you can write in 1 or 2 lines, and then call that a description of things that exist in the universe. And the fact that we have Schwarzschild is already magnificent. People have wrote thousands of papers about this, and Kerr already has almost another 1,000 of papers, right? So these rotating black holes happen to be all over the place in the universe. We believe that there is one in every direction of the sky because there's a galaxy, and in the center of the galaxy, there is Kerr. And the fact that we can even make predictions about these things using a 2-line equation is quite a miracle of our description, independent of the astrophysics that obviously are present. So it's worth the time to study what kind of exact GR solutions are, even before we think about whether they can be realized in the center of a galaxy or not. So as I said, one of those examples is a Taub-NUT solution. It's a solution that has mass equal to NUT charge. We already see that Taub-NUT is in a sense more symmetric than Kerr. So Gibbons and Hawking, when they derived these solutions, they were looking at spherically symmetric ansatz that have a NUT charge, and they found that kind of like Schwarzschild, Taub-NUT doesn't have a sphere, but it has an ADS tree. And that's interesting. The U1 here is just the time direction in Euclidean time. This is just a cycle. But the ADS tree is kind of playing the same role as the sphere in Schwarzschild. So this is actually more like Schwarzschild. Nevertheless, you can add a spin to Taub-NUT, and you can add NUT charge to Kerr. And in fact, it so happens kind of remarkable that when you add NUT charge to Kerr, then it becomes Taub-NUT. Sorry, let me just write that a bit more clear. I thought I mentioned it here, but yeah. So imagine that we have Kerr. So Kerr has a mass and a spin. But now if we add certain NUT charge, and then we look at the extremal Kerr, then we just describe that in terms of 2 parameters, m and n, because we are setting the temperature to 0. And it just happens that that solution is a Taub-NUT solution, where the mass of the Taub-NUT solution is the NUT charge of Kerr, and the NUT charge of the Taub-NUT solution is the mass of Kerr. So like the first time I gave this talk, some people would complain, Taub-NUT